Hi, I'm RayTu, and I am a faculty member in the Chemical Engineering Department at the City College of New York. This is a short little video that's going to describe a couple of the research projects that are going on right now in my lab. First, I'll discuss just for a second my background. So I'm a chemical engineer by training. I went to the University of Florida for my undergraduate degree. At the University of Florida, I briefly did some research thinking about how it is that biological molecules and microbes could absorb to silica particles that are coated with metal for tertiary filtration. After I finished at the University of Florida, I went to the University of Minnesota for a short time. My advisor at the University of Minnesota, Matthew Terrell, became the dean of the University of California, Santa Barbara, and I went along with him. And most of the work that I did at UCSB thought about how it is that you could design biological molecules using a rational design technique to try to isolate those molecules at interfaces. And once they're at the interfaces, how do they present both the hydrophobic and hydrophilic portion of those molecular designs? After that, I went to the Georgia Institute of Technology, Georgia Tech, and when I was at Georgia Tech, I worked with Victor Breedveld, really thinking about a tool to quantify rheological properties of biomaterials, so microrheology. The common theme in all of these projects is something that is borne out in the research that I do now, which is how do biological macromolecules act at an air-water interface. So I'll talk about a couple of those projects now. So the first project that I'll discuss is the rational design of a helical peptide, where that design can allow one to understand how adsorption of that interface controls the folding of that biological molecule. And so what we've done is we've designed a set of molecules that form a helix, and once they form that helix, there's a hydrophobic face to the helix and a hydrophilic face to the helix. So what you're looking at on the left side of this image is the alpha helix, and what you're doing is you're looking down the z-axis of that cylinder of the helix, right? Shown in yellow are the hydrophobic amino acids, and shown in blue are the hydrophilic amino acids. When those hydrophobic amino acids come together in the helix, they define about 180 degrees of that face of the helix, and that side of that helix will partition to the air-water interface. The hydrophilic side, well, that can be charged, it can be polar, and it can define the hydrophilic side that actually sits in the water. So what one can do with this design is you can really push for folding being simultaneous with adsorption to the interface. How you can use this, for instance, is you can couple these peptide systems with a liquid crystal system, and then you can look at the adsorption dynamics, and that's what's being shown at the top right. At the top right, what we're doing is we're looking at how it is that you have increasing concentrations from the bottom row to the top row, where the top row has the highest concentration, the bottom row has the lowest concentration of these helices, adsorbing to a liquid crystal interface. And what you see is a transition of the liquid crystal. So this is a liquid-liquid interface now, the liquid crystal interface against the water interface. And so those molecules, once they jump to that interface, transition the liquid crystal from a homeotropic phase, which is in black, to a planar phase, which is this much more colorful yellow image going on the right. So from left to right, what you're seeing is an increase in time. So not only can you measure when those molecules get to that interface, but you can see how it influences the liquid crystal behavior. So not only have we done this with molecules, but we've also done this with particles. So you can think of an anisotropic particle being analogous to the helical polypeptide. And so on the bottom right, what we have is a Janus particle, and this is work that I'm doing in collaboration with Professor Kretschmar, also in the chemical engineering department at City College. And she makes these Janus particles where one hemisphere of that particle is hydrophobic, shown in yellow, and one hemisphere of that particle, shown in blue, is hydrophilic. When you get these molecules to jump to the interface, what winds up happening is they partition to the interface, and they can give that interface interesting materials properties, right? So once those once those particles get to the interface, you can compress them on a Langmuir-Blodgett trough, and you can watch the instabilities occurring. And in this case, you can see behaviors like wrinkling and folding, but also once those particles get to the interface, they can actually create a stiffness at that interface, and then the defect structure can promote behavior like subduction. So we can really be quantitative about this behavior by putting these particles, once they're functionalized in an anisotropic fashion, at the tips of AFM cantilevers. When they sit at the tip of the AFM cantilever, you can control the degree both of anisotropy by controlling the hydrophobicity and its orientation. Once you do that, you can actually take the particle and push them into the interface. And as you lift them out of the interface, you can measure the different forces that occur because of the presence of that anisotropy at the interface. And this is work that we've done in collaboration with Ray Dagenstein at the University of Melbourne. And the images that you're looking at the bottom are the various orientations of those particles as they sit on the ends of the cantilevers. So a last effect that you can have when you actually conjugate the polypeptide with a polymer group is you can effectively make a tri-block polymer. And once you do that, you can actually study the differences between intermolecular self-assembly and intramolecular self-assembly. And we do this by making 4-arm blocks and 2-arm blocks of these helical peptides that want to self-assemble because of those hydrophobic groups. And then we can look at how they come together, how fast they come together, and then how different counterions, different salts, wind up influencing the rate that they come together. So the next project I'll talk about is a collaboration that has occurred with Argonne National Labs, specifically Sector 15, NSF's ChemMat CARS, which is with the University of Chicago, and the pharmaceutical industry. So in the pharmaceutical industry, more and more of the molecules that they're using as therapeutics are biologics, meaning they're large macromolecules instead of small molecules. And these large protein-based molecules have a different set of concerns in formulations and processing than small molecules. Namely, once they get to the interface, it's unknown whether or not you get a tremendous amount of unfolding, whether you get a sequestering of those molecules from the liquid phase, whether you get precipitation. And once you get all those behaviors, if you lose the efficacy of the drug. And so this is a problem that can be solved by adding surfactants to the solution and therefore creating a situation where you have competitive absorption for those interfaces. And this could be a liquid-air interface or it could be a liquid-solid interface. And so what I'm illustrating on the left is both those molecules, the surfactant molecules shown in yellow and blue, and a large monoclonal antibody shown very colorfully near the middle. And they compete for that interface. And really the question is, well, who wins in that competition once they try to get to the interface? And then once they're at the interface, to what degree does the unfolding of the protein promote unwanted aggregation sorts of behaviors? And so this is when the collaboration with Argonne National Labs comes into play. So at Argonne National Labs, we can do an X-ray reflectivity experiment and look to see exactly who is getting to the interface, but then also look at the orientation and the unfolding behavior at that interface. So those are the two projects I wanted to describe. Again, this is research that's done in my group, RayTu, at the City College of New York. And if you have any questions about this research, what I have is my email address at the bottom left corner, and you're welcome to ask any questions whenever you want. Thanks for paying attention.